Hello, everyone. So let's get started. Thank you. So hello, my name is Anton, and I'm here today to talk to you about automatic front-end generation for RISC V extensions. Or, in other words, we want to go from a machine-readable ISA to a version of QEMU along with a set of tests that we can use to verify that the conversion from ISA to QEMU is correct. And this will end up being very useful in early stages of development for a new ISA, particularly for testing, as we'll see later on. Firstly, some formalities. I work for a company called Revenge Labs based here in Milan. We do focus primarily on a decompiler that is built on top of QEMU and LLVM. And on the side of that, we also do consultancy on compilers, emulators, and dynamic binary translation. Now, I want to start this talk by doing a brief recap of a tool called helper-to-tcg, which will be very central to this talk. So, around 2 years ago, we did a presentation at the KVM forum introducing helper-to-tcg, and this talk is very much a sequel. So I want to recap some just facts about helper functions and TCG, and also helper-to-tcg. So say you have a predicated add instruction that you want to add into QEMU. You generally have two approaches to do this. One is to introduce a helper function. This is just a normal C function that you would compile into QEMU, and whenever you decode the instruction that you've added, you will end up calling this function. The other method is to introduce tiny code via tiny code generators. So this is, again, a C function, but you write these TCG gen calls, which creates the QEMU intermediate representation. And this then gets mapped to whatever your host architecture is. But what really is the difference between these two? And a good method of finding this out is looking at host instructions. So we'll briefly talk about a hexagon instruction for a predicated add. This is the assembly for it, if you're familiar. If we go ahead and look at the host instructions generated for the helper function implementation, we'll see a block of code at the top. It's just a bunch of moves. You shift data from memory into host registers. And then you see a call instruction. This will call our helper function. And if we inline just the helper function here, you can see that we end up with an addition followed by a conditional move. And then in the end, we end up shifting some data back into memory for the CPU states. Now, for tiny code generators, we see something similar. We end up having a few moves at the top, shifting data. We then have an addition and a conditional move, and then we shift data back at the end. Now, the real difference is when you start introducing constants. So here we have R1 is 1, R2 is 2. So if we add them, we get 3. And the predicate is set to hex FF, so we end up taking the branch. Now for helper functions, you see pretty much the same thing. We shuffle data, we take the call, and the problem here is that the call instruction will inhibit optimization across that boundary. Whereas for tiny code generators, we end up getting just 2 moves out the other end, and this is due to the tiny code optimizer doing constant propagation for us. So to summarize, helper functions are a lot easier to implement, but you lose out on a lot of optimization due to these call sites. Whereas for tiny code, you get constant propagation, then code elimination, and a few other optimizations. The only downside is that it's a bit more tedious to implement, and it's easier to mess up. And this is where helper-to-tcg comes in. We want to take one of the implementations to the other. So if we look at a quick example, we want to go from C code to LLVM IR. We can do this by just feeding it through Clang. We then want to go from LLVM IR to tiny code. And we do this through the helper-to-tcg tool, which is an IR to IR translator. So if we look at our predicated add, we have it here in just a normal helper C code. We get the following LLVM IR. You don't have to focus super much on it, but we have an addition and a select, so conditional move. And then we end up with the tiny code on the other end, which is pretty much a one-to-one translation if we go back and forth. Yeah, most of the instructions are there still present. So to recap, it is a build time tool for going from LLVM IR to TCG. We previously applied this to the hexagon frontend and translated around 1,400 helper functions. And this is a project that is actively trying to be upstreamed. So we want to introduce it as a QEMU sub-project, meaning you can use it for translating helpers already present in the code base, or you can use it on the side if you have a C function that you want to convert to tiny code and then clean up maybe and include into QEMU. We sent an RFC last year, but since then we've been trying to make sure that this tool actually functions correctly across multiple architectures. So now, finally, back to RISC V. I want to introduce you to the XQCI and XQC comp extensions. And these are extensions developed by Qualcomm. They're actively being developed with the goal of improving instruction density for their microcontrollers, as usually is the case. If you execute less instructions, you hopefully consume less power and hopefully get more performance. XQCI introduces a 16, 32, and 42-bit ISA and is focused mostly on arithmetic. So you have saturating adds, saturating subtractions, loading of wider immediates, which is why you need the 48-bit ISA, and fused multiply adds and so on. They also have the XQC comp extension, which is a variation on the existing SED comp extension, which introduces stack frames and double moves. Now, XQCI is being developed in the open, and its first 0.1 release was in August 2024. We got involved pretty early on, I think in September, around version 0.2. And at this point, we had no toolchain support for the extension whatsoever, and it was actively being iterated upon. So what is the benefit of involving QEMU at such an early stage in development? One is that if we're able to go from this machine-readable ISA to a working version of QEMU, you can quite quickly prototype instructions and explore different implementations of the same instruction you might be interested in. We're also able to validate the versions of the spec across versions, and we do this by generating tests for one version of the spec, and then when you update, you can run your new version of QEMU against the old tests. You will get some failures, but you can verify that the failures you get are only for the instructions which should have changed. And by doing this, we were able to catch a bunch of bugs in the upstream repository for the spec when updating versions. And then once we finally start getting toolchain support for the extensions, we can immediately start testing them against existing test suites. So the goal for this project can be summarized as producing a version of QEMU for each version of the XQCI and XQC comp spec. Now let's take a look at the actual specification for these instructions. It's a part of the riscv-unified-db. And the goal of this project is to act as a single source of truth for RISC V extensions. And the primary focus here is to make sure that everything is machine readable. So you have definitions of everything from instructions, control and status registers to extensions. So you also have information about what extensions depend on other extensions, etc. And this project also includes backends written in Ruby for various things, that including specifications, just like PDF documents, HTML documents. They also verify the implementation of instructions that they have present, and the goal is also to get an instruction set simulator as a part of this. So I do want to give some credit where credit is due. This project is headed primarily by Derek Hauer over at Qualcomm and Afonso Oliveira over at Synopsys. If this is something that interests you, I'd urge you to check out their 2025 FOSDEM talk, or just head over to the repository and check around. So let's take a look at this specification. It's a YAML file that contains the following keys. If we look at an example of instruction, we can see, for instance, that we have the short name of the instruction, we have some longer names, a description. This is useful for generating documentation. We also have information about what extensions define this, so we can see that this particular instruction is defined by XQCI or the sub-extension called XQCI-AC. The base is 32, meaning the size of general purpose registers. We also have information about how the instruction is encoded. So we have the fixed bits along with what fields are variable and where those variable fields are encoded. And finally, or not finally, one more, but we have some information about how the assembly of these variable fields should be printed, and then some information about what privilege modes this instruction is available in. So SU is for supervisor and user, VS is for virtualized supervisor, virtualized user, and machine mode is implied. And at the bottom, we'll see a snippet of code defining the semantics of the instruction. This is a very C-like language. It's more closer to C++, but we'll talk a little bit more about this in a bit. So how do we go about going from this specification in the unified database to a working QEMU version? We have three main considerations. One is handling just the definitions of instructions. We try to do this in TCG. And then we also need to be able to decode the instructions to call into our generated TCG code. And then also disassemble the instructions for pretty printing. And finally, we need to be able to deal with control and status registers, so how these are defined and how you access them. If we take a look at instruction definitions, here we have the previous instructions you saw. So it's a fused multiply add. Now, as I mentioned, this is very, very close to C, or rather very close to C++ if you look at more complicated instructions. So if we have C++, well, then we have LLVM IR. And if we have LLVM IR, well, then we can use helper-to-tcg. So the workflow looks like this. We start from the unified database. We generate some C++ code by doing some simple just text transformations. We feed it through Clang to get the LLVM IR. And then finally, we want to end up with TCG code at the end. So looking at our multiply add instruction here, we have the C++, or like the unified database. We end up with some C++ code that is almost identical. So the fields of the instruction are turned into arguments. And then the final write of the GPR here at the bottom is turned into a function call. So we want to differentiate between reading and writing from GPRs. We turn this into LLVM IR. Looks like the following. You don't need to focus too much on it. And then at the end, we get TCG. And here you can notice that at the top, we do some reading from GPRs. We do this by calling the xqci get GPR function. And at the end, we write back to the GPRs, but we write back to the global array called CPU GPR. So this is why we distinguish between reads and writes. So that allows us to handle instruction definitions. We simply include these into QEMU. What about decoding? If we look at the decoding section of the spec, thankfully, this is very, very close to something that QEMU can already do, and mapping this to the decode tree format is very straightforward. And so this is a format that QEMU already supports. You can include this, run the decode tree Python script, and you get a decoder in C. The only real other thing to consider is that this decoder needs to call out into something. So we need to generate two other files to deal with this. One provides functions that are being called for decoding for execution. So at the top, you have an if statement that simply checks that the extensions are available. Then you have a call to qc mul-iad, which is our generated TCG code. For the other file, then this is when we decode for disassembly. We instead of taking the disascontext struct, we take a struct provided by the RISC V disassembler. We just fill out some fields. And this allows us to get pretty printing out on the other end. So lastly, what about control and status registers? You know the deal at this point? It's the same. We look at the UDB. This is the specification for a CSR, which I didn't discuss previously, but it's very similar. We have a name, a long name. We have the address of the CSR, its size, what privilege mode it's available in. We also have information about what extensions it's defined for, and finally at the bottom we have the fields of the CSR and what bits they're set at. So we take this, we generate some C code on the other end. We get macros defining the address and the masks of the CSR. We generate a function for a predicate to check that the extension and privilege modes are correct. And then we get a simple read-write function for modifying the field in the CPU state corresponding to the CSR. So that is pretty much the last piece of the puzzle. We can include all of this into QEMU, along with some glue code, which we can also generate, and off we go. There are some main challenges here. One is that for CSRs with custom logic for reading and writing, that is just not something we handle at the moment and implement manually. And one other thing we had to work on was making sure that helper-to-tcg could output TCG code that can be embedded nicely into the RISC V frontend. And this primarily involved making sure that we can get these calls to functions which are not declared during translation of the IR and make sure that we get the correct outputs. So this is a function that takes immediates as input and outputs a TCGV, for instance. And we need to make sure that this didn't inhibit any sort of optimization. So some status updates. At this point, We had to make some slight modifications to the RISC V frontend, primarily for adding support for 16 and 48-bit dynamic decoders. So the RISC V frontend allows extensions to define what decoder they want to use, but this was only possible for 32 bits. We had to add some fields in the CPU state and generate some glue code. In the end, we ended up with the following statistics. So for XQCI, we have 22 16-bit, 110 32-bit, and 25 48-bit instructions. And for XQC comp, we have 7 16-bit ones. And this brings us to the final and large part of this talk, which is testing. Here we had two approaches. We wanted to make sure that a single instruction is implemented correctly in QEMU as described in the spec. And then we also wanted to run it against existing test suites. So for generating single instruction tests, I want you to recall that we can produce LLVM IR. And since we can produce LLVM IR, there is a whole suite of tools we can use. And one of these in particular is called CLE. CLE is a symbolic execution engine on top of LLVM IR. So you specify what variable you care about, and you then run CLE on the LLVM IR, and it will go through your code, and whenever it encounters a branch, it adds that as a constraint to a SAT solver. Then running the SAT solver, and out on the other end, you get a value for those constants that take every single branch through your code. So as a quick example, this is a little bit of a dummy example, but we have a variable x, and we print first branch or second branch, depending on the value. The value of x is set by the CLE make symbolic call. So if you compile it as a program, you can link against CLE, and then CLE will provide a constant. If you compile it to LLVM IR and run it through CLE, then that's when it does the SAT solving. So if we do the SAT solving, we'll get two test cases, one where x is 0 and one where x is 24. Meaning we take the second branch and then the first branch. So if we were to compile it and run the tests, this is what we would see. A slightly more complicated example. We have an add instruction that just adds two numbers. We have two symbolic variables. And then we just print the constant or the result of the addition at the end. If we were to run this through CLE, we would get a single test case where A and B are 0. This is because there are no constraints in the code. There are no branches. So we would get just C is 0 as output. Now, what if we just add a dummy branch? We just add a branch that checks if an overflow has happened or not. And then we write to some global to make sure nothing gets optimized away and print it at the end. If we do this, we'll end up with two test cases. One where the path of overflow is not taken, so A, B, and C are 0, and then one where we get an overflow. If we run the program, we would see that we get a second test case where C is a large number, so an overflow occurred. And this is the method that allows us to generate edge case tests for all of the instructions we care about. So we can repeat this for other arithmetic operations like multiplications, divisions, etc. We can also do it for loads and stores. So instead of checking for an overflow or underflow, we can make sure that the address of the load and store falls within some range we control. So whenever we take all of this output and produce a test out of it, we can make sure that that address range is mapped to something. And if we also track values being loaded and stored, we can make sure that you get correct read and write behavior. Similarly, for jump instructions, we can just make sure that the destination address is within some offset of the jump. And that way we can use it for taking branches and checking output. So we take the output of these CLE tests and we produce two sets of tests. One is just a raw ELF binary, which requires no toolchain support, meaning we take the encoding from the spec and we just dump it, or fill out an instruction, dump it into the binary. And this is what we did initially to make sure that our implementation in QEMU was correct when we didn't have any toolchain whatsoever. Then we also produce C tests with inline assembly that check for the same thing. So in the end, we got 293 raw binary tests for XQCI, 42 for XQC comp, and then 117 C tests for XQCI and 2 for XQC comp. So I want to show quickly just what this looks like. So what we have here is just a YAML file. This is what CLE would output. So each section from variables until here is one test. So the first test is input value 0, other input value 0, output is 0. Second test is an input of a large number, and we expect some overflow to occur. We actually have 3 tests where we expect an overflow to occur. And if we were to look at, oh, well, that's not the one. That is the one. If we were to look at the semantics of the instructions, so we have 3 overflows. One occurs in the multiplication with a constant. One occurs in the addition of those 2 values. And then we have a third test that checks for overflow on both of them. So this has been incredibly useful for finding bugs, not only in helper-to-tcg, but also in the spec upstream. I can also show you what we generate for testing. So this is one of these inline assembly C tests. So you can see that we run the molIAD instruction, providing some input and output, and just check that the outputs are what we expected them to be. I'm going to see if I can do this with one hand. We can run, yes, that's correct. So here we're running the molIAD C test that I just showed you. We're enabling the XQCI and XQC comp extensions and disabling some other ones because we don't do this implicitly at the moment. So here we're just checking the input assembly. So we can see that we do get some pretty printing for the output. I think there's something strange going on with how we print the registers, but that will have to be fixed. If we go ahead and just check also the tiny code, we can see if we scroll up a bit. Okay, so we have a molIAD instruction at 10E8. If we check 10E8 down here, we get the multiplication and the add and the move. And so this is something that we repeat for every single instruction in the spec. Oh, sorry. So what about dealing with existing test suites? This is something we also want to work on, but this requires toolchain support. So once we start getting toolchain supports for a subset of instructions, we start running them through spec and mbench and picobc we're working on. But this has allowed us to find discrepancies between how the compiler implements the instruction and what is present in the spec. And often, more than not, it ended up being a problem in the spec. So finally, I want to round out the talk by just taking a look at some what we plan to do in the future with this, and a quick summary. So we've been able to go from a machine-readable ISA to a version of QEMU for every single version of the spec, and along with the set of tests. And this has allowed us to catch bugs early on in the development of the specification and also iterate on instruction implementations. Now, going forward, there are other applications for this. For instance, the UDB contains specifications for all of the standard RISC V extensions, not the vector ones at this point, I believe, but most of the standard ones. So we could easily use this to also generate more tests for those and make sure that the spec also agrees with QEMU, for instance. We also plan to work on testing system mode more thoroughly. So currently we run the semi-hosted picobc tests and get some failures there. And then another option to explore is looking at CSRs. So if a CSR has a custom read-write function, we can feed that through CLI, and we can make sure that we get inputs to the instruction which trigger edge cases in the CSR. So finally, for upstreaming, we want to open this up to a discussion a little bit. So there are 2 main dependencies on this project, being helper-to-tcg and the unified database, and helper-to-tcg depends on LLVM. So one option is to include both of these sub-projects and then make the extension optional. Another, simpler one would be to simply commit cleaned up generated code, which I know is a big sin, so that's why I'm asking for a bit of input here. If you have any strong opinions on how we should go about upstreaming something like this, please feel free to reach out. And that has been it for me. Thank you all for listening.
Hi, good talk. So I spent a long time a couple of years ago benchmarking RISC-V-TCG. I do remember that helper calls dominated a lot of those traces. Could you talk about the limits of what instructions you can and cannot generate? For example, floating point, vector, and things like that, which are traditionally, I think, all helpers at the moment. You know, what are the limits of the RISC V architecture that you could or could not generate and test?
I think generating support for vector instructions is absolutely possible. Floating point is not something we do at the moment. And then we also we make some assumptions in helper-to-tcg on how the IR is structured. So one assumption we make is that after the LLVM optimizer is done, we end up with a loop-free code pretty much. So loops get unrolled or rolled into vector operations. And if it doesn't, we don't emit TCG for it. We did the benchmarking for Hexagon a while back, comparing helpers and TCG, and you saw some instructions where it was like a massive boost in performance going to TCG, and some where it was slower. And I think you just have to do a bit more like a case on case, on a case by case basis. Okay, if there are no other questions, then thank you.